Today, under the topic of thermodynamics, I'll be explaining how to calculate the bond energy or the bond enthalpy of a reaction. This is part 1. Actually, there are two different ways I can show you this. This first part is showing you the total breakdown of all the bonds between the reactants and total formation of all the bonds within the product. So whenever a chemical reaction occurs, heat energy is absorbed into the reactant so that their bonds break, and then once the bonds break and reshuffle, products are formed. When products are formed, heat energy is given out of the system. Now, the two formulas that I have written on the board, the one on the top is called a molecular formula because it actually shows you the molecules, and the second formula that I have written on the bottom is called a structural formula. So what a structural formula shows you, actually the bonds in between the molecules, the bonds on the reactant side and bonds on the product side. So I have taken a specific example of formation of water molecule. There are three steps that we can take in order to calculate the total enthalpy change of this reaction. So step 1 is on the reactant side, step 2 is on the product side, and step 3 is dependent on step 1 and step 2. So for the first step, the two molecules of hydrogen are held together by a single covalent bond. They will take in energy from the surrounding and break the hydrogen to hydrogen covalent bond. So there are two molecules, so we'll calculate the amount of heat energy that it absorbs. So I have placed 2 multiplied by 432. This 432 is a average bond energy, average bond enthalpy. That is the amount of energy held inside a hydrogen to hydrogen covalent bond. So 430, these values are all established. So 432 multiplied by 2 for hydrogen to hydrogen gives me 864. And then oxygen to oxygen double bond, it has a 495 kilojoule per mole heat energy contained inside. So oxygen molecules are going to absorb 495 kilojoules of heat energy per mole from the surrounding. And the total on the reactant side is positive 1359 kilojoules. So I place a positive sign in front of the reactant side total because heat energy goes into the system. This is the system, heat energy goes into the system in trying to break the bonds. Let's see step 2, where step 2 has the bond energy released out of the system. These two steps, step 1 and step 2, are totally opposite to each other. So the products are exothermic reaction where heat energy has to be given out to the surrounding. So oxygen to hydrogen is 1, 2, 3, 4 similar type of oxygen to hydrogen covalent bonds. So each oxygen to hydrogen covalent bond has an established 467 kilojoule per mole heat energy related to it. So 4 multiplied by 467, we end up with a negative 1868 kilojoules per mole. I have placed a negative sign. Since both the sides are quite opposite, this side has plus, the other side will have a negative sign. Negative sign indicates that this reaction is exothermic. It releases heat energy out into the surrounding. So moving on to the third step, which is very crucial. So the third step calculates the overall enthalpy change of the reaction. So the formation of water molecule on the reactant side versus the product side. The reactant side absorbed a total of 1359 kilojoules of heat energy from the system. We will add it to the amount released. The amount released out into the surrounding is 1868 kilojoules. So adding both of these established exothermic and endothermic reactants and the product side, we end up with a negative 509 kilojoule per mole. There are two things associated with it. First, the negative sign. The negative sign for the heat of formation of water molecule indicates that this reaction overall is an exothermic process. When I say exothermic process, I mean 509 kilojoules of heat energy is given out to the surrounding. The overall amount of energy associated with the formation of water molecule is 509 kilojoules of heat energy given out to the surrounding per 1 mole of water molecules being formed.